recording. Okay, so good evening, everyone. I would like to thank all of you to be with us today in this Athena European University Colloquia talk in teaching science. I hope wherever you are, the weather to be less warm than here in Greece. I'm in Athens right now, and it's 40 degrees. So it's nice to have to be inside with the aircon and listen. You know, a good friend and a good colleague, Dr. Nissim Harel, who is a senior lecturer in Holon Institute of Technology in Israel. Nissim has done, his resume includes high quality studies. Like he has his bachelor degree in electrical engineering from Technion in Israel, then his master's degree in electrical engineering in Georgia Tech. Let me also accept the people. And then, another master's degree in computer science in Georgia Tech in USA, and then a PhD in computer science from the same university. And the title of his thesis was Memory Optimizations, the Distributed Stream-Based Applications from Georgia Tech, as I mentioned. Nissim also is a part of a project that we run together, the ITEM project, Innovative Teaching of Educational in Mathematics, Innovative Teaching in Education in Mathematics. And today he's going to talk to us about his work in teaching mathematics in the 21st century. So the floor is yours, Nissim, and we would like to thank you once more for your kind acceptance to be part of this initiative. You are muted, and now you're ready to start. Thank you.
So first of all, I apologize. I'm after a cold, so I will I will cough a lot. So first of all, hello. I will talk about our experiences in implementing changes into the way we teach mathematics in the framework of the project Kostas talked about, ITEM, an Erasmus capacity building project that aims at improving mathematics teaching in higher education institutions. Mainly, I will discuss why and how real-life problems should be integrated into lectures in mathematics and how to do that. So first of all, we need to discuss about the problem with math, why there is a problem in math studies. So the thing is that most of the students preparing for an engineering or computer science degree don't seem to like mathematics too much. They sorry. They underappreciate the importance and the role mathematics plays in solving real life problems and applications. They remember their mathematics studies in high school as some kind of an endless series of technical drills. They recall the stress that accompanied math studies when everybody told them that this is a very important subject and it's very crucial for their professional success. And they obviously believed it and internalized what they were told, but never really understood why this hard subject is so important. When these students start their studies in engineering, they're again being told that mathematics is important. They look at their class schedule and find out that mathematics courses form the backbone of their first year studies in STEM subjects, and sometimes they will have 6 math courses in the first year alone. So they have a low motivation to study, and this is a demanding subject, and this leads to the inevitable results. Many students do not properly understand what they learn, and as a result, they do not recall and cannot apply math knowledge in their second and third years of studies, as well as in their professional career. No surprisingly, math courses are also blamed for being a leading cause for student failure to meet the requirements of first-year academic studies and ultimately to graduate. So we think that this is unfortunate and unnecessary, that students who wish to study computer science or engineering, or in fact any other STEM subject, will abandon their dreams because of failure in mathematics studies. Further, we think that poor achievement in mathematics and the fear from mathematics are mainly the result of the way mathematics is being taught in high schools and in higher education institutions. And this is why we started the item project. Our goal is to demonstrate to the students that mathematics is relevant to the program they have chosen to study, and that they have the ability to learn mathematics and succeed in learning the subject. Uh, um, Before I delve into the talk, I want to stress that we understand that there is no silver bullet or a single simple fix to the problem I described. Rather, we propose to adopt a confluence of teaching and learning activity techniques that will engage students and provide them with combined learning strategies that will help them to better understand mathematics, better and more precisely formulate mathematical concepts, more efficiently look for ways to solve problems and increase their capacity to apply earned skills and knowledge. These strategies are intended to promote students' understanding and their abilities in logical thinking and creativity. So what are we suggesting? The item approach has four main principles. The first and foremost and the most important one is that the course should be interesting. Our experience in teaching shows that students are interested in topics that they find relevant to their profession, to their lives, and therefore we try to teach math through real world, real life problems that the student may encounter in their professional lives. Through these problems, we will present the mathematical concepts and the required proofs, and I will show some examples of that shortly. The second principle is building the students' confidence in their ability to succeed using an independent or a pair learning practice during recitation. So the idea is to show students that they actually can do that. This is not it's not that it's not difficult, but this is doable. They can learn math and understand it. Unfortunately, being interesting and relevant is not sufficient. Some students arrive to the higher education system with low learning abilities, which hinders them from learning and understanding math courses. So for these courses, students, we must offer a different method for learning math, and most importantly, what to do if they get stuck. So we need to explain them how to study math because they were not trained to learn this subject properly. Additionally, quite a few students realize that they are in trouble only towards the end of the semester. Even if they somehow manage to pass the course, they do not understand in depth and will not be able to use this knowledge in more advanced courses. So students must receive feedback that reflects their true level as quickly as possible. So until now, we discussed measures that aimed at nudging the students to take actions and help themselves improve their level of understanding in math. But for some students, there is a need for active measures. We must proactively identify students at risk to fail as early as possible and provide them with mitigation options and solutions. So I will discuss each one of these principles, but the main bulk of of my talk will be demonstrating relevance, real life needs as motivators for developing new mathematical concepts. So, in a sense, how do we demonstrate relevance to the subject matter while teaching math? We use real-time examples to explain where the current mathematical topics is being used in real life. Whenever we can, we prefer an example from the subject matter students decided to study. as opposed to the way the subject is being taught in many applied mathematics textbooks, we try to present the real-life problem as a prelude and as a motivation to the mathematical topic learns, and not just as an epilogue after the mathematical topics have been introduced, taught, and practiced. So I will show the difference with an example. I will show you how a topic is being taught traditionally, what is being done in terms of providing an example after the subject has been taught, and how we can teach the subject and provide an example even before the subject has been taught. So when the teacher demonstrates the relevance of a mathematical topics to the subject the student have chosen to specialize in, it becomes more appealing to students, since this is the field the student decided to study. So that means for the students that the effort they invest in learning mathematics is not futile. The knowledge they gain will not only suffice to pass the mathematics exam, but will help them in their later classes and their professional career. If the teacher is consistent in showing the connection between mathematics and the subject the students want to specialize in, the student will understand that mathematical knowledge is not a foreign element in the curriculum. Rather, mathematics is critical to the understanding of the core courses in the student desired field of knowledge and to their professional success. So I will start with an example of a system of linear equations. This is one of the first topics that are taught in a linear algebra course. And this is the way it's been presented in textbooks and in many linear algebra classes. So we have a definition of a linear equation. A linear equation is basically you have several variables, x1 until xn, and then you have a1 to an, which are constant, and multiply these are the coefficients. They multiply the variables, and this is a single equation, and we can have a system of these kinds of equations, and we can solve these equations, and we learn several ways to do so during the class. Now, what I want to do is ask the question the students probably ask themselves: why on earth do we want to solve a system of linear equations? Where they are being used in practice? Can the student expect to encounter these equations in their professional life? Apparently, the answer to these questions is usually not provided, at least not at this stage of learning. Students are asked to learn methods to solve these problems and prove that the methods work. Now, once the students have hopefully mastered the methodology of solving a system of linear equations, then the lecturer proceeds to the next topics, because there is no time. There's a lot of material to cover, so little time, and there is a need to finish the curriculum. So in some classes, more as an appendix to the topic, and before proceeding to the next topic, the lecturer will give a short example describing where the topic is being used. For example, I will show an example of using linear equations in balancing chemical equations. So then we will see something like that. There is a chemical equation. You have a reactant side and a product side, and you want to know how many quantities you need of each one of the elements in order to get in the reactant side in order to get the product side. And what we're doing is we model the problem using a system of linear equations. And what do? We say that there is a variable x1 that multiply the nitrogen. We have a variable x2 that multiply the helium, and then we have a variable x3 in the product side, and the atoms of each one of the elements need to be the same. So when we do that, we get for the nitrogen 2x1 equals x3 and 2x2 equals 3x3, and then we know how to solve this, and then we get into the balance reaction. And this was a very simple example. We can go to a more sophisticated example, a more complex example, more complex reactions, and there we will need a more complex equations, and these are the equations, and we know how to solve this. This is how we solve it, and we end up getting to these equations, and this is what is being presented after the fact, after the students already mastered, hopefully, systems of linear equations, how to solve system of linear equations. Now, it is great to see this example, but it will be better to show this example as a prelude or a motivation to the topic. I will soon show this example being presented as a prelude to the topic. Obviously, we will not solve the equations. However, I think that before presenting the specific example, the teacher may use the opportunity to discuss one of the roles math plays as a modeling tool to many problems in real life, in real world situation. A system of linear equations is just one example of the use of math to model real life problems. Models are using systems of linear equations themselves are being used in many problems as well, problems such as machine learning, networking optimization, etc. So balancing chemical equations is merely one example of the use of systems of linear equations. Also, it should be presented to chemistry and life science students. Computer science and engineering students should be presented with examples from their fields of studies. So assuming that we're talking about chemistry and life science students, how do we want to present this material as a prelude? Now here we are not going to solve the problem. What we're going to say is that we're going to explain the problem. Here is the problem. We want to balance the reactant side and the product side, and we want to make sure that each one of these elements will be similar in both sides, and then we solve it. Now here we can solve it by guessing. If 2x1 equals x3 and 2x2 equals 3x3, we can guess that if we have 1 N2 plus 3 H2, we will get 2 NH3, and this is what we want to get, and everything is fine. But when we get a more complex chemical reactions, it's very difficult to do that. Now we get these kinds of equations, and for this, we will need analytical tools in order to solve the problem. And what analytical tool can we have? We will define this as a system of linear equations, and we will see how we can solve it. So this is as a prelude. This is a better way to show relevance before the topic is being presented. And here we don't have to go into the details of everything of the solution, because the details will be presented later. Now the students know that there are practical problems that they actually will use when they have learned this stuff, and they're going to use that in the future. And this is great. But the question is, can we get better than that? Can we do better? And we think that curiosity-based learning is better than presenting the subject beforehand. And what do we mean by curiosity-based learning? What we mean is that we will present the topic and the mathematical theory and the mathematical notations through a real-life problems. And I will demonstrate it through the concept of vectors. So this is the way vectors are being presented. This is a standard way to teach vectors in the math class. And the lecturer presents a definition, explains the definition, what it means. This is a tuple, blah, blah, blah. And then provide some examples. This is a two-dimensional vectors, a vector, and a three-dimensional vector, and a four-dimensional vector. But instead, we suggest getting to the mathematical concept through a problem. For example, we have a candy factory which produces a number of products in different packages. The question is how to build an automated system that will help us identify the package in order to assign the appropriate barcode for each package. So now this question has nothing to do, at this stage, has nothing to do with vectors. Actually, vector will be a solution, how to model it. So first, to solve the problem, we first need to understand how to describe a package. So how we describe a package? We describe a package when each package, we understand that each package has characteristics such as length, weight, and we will describe the package using these properties. In the world of data science, these characteristics are called features. So we will describe a package using its features. And now, for the purpose of this exercise, we will choose 4 features: length, width, height, and weight. Hopefully, this would be sufficient. So this package, you can see here in the image, has a height of 2 centimeters, a width of 5 centimeters, a length of 12 centimeters, and 250 grams of weight. And then the question is, okay, we have this. How do we want to describe each package like that? Maybe there is a more convenient method to describe the features of different packages. And then we get into the concept of a vector, which is so the conclusion will be that a more convenient way to represent features of various packages is using an ordered series of numbers, and this is what we call a vector. Now that we understood what a vector is and it is used, at least for one example, we can provide the mathematical definition of a general vector that is easy to understand in the context of the example. Now we can go to other concepts. So until now, we succeeded in describing the various packages. So this was one part of the solution. But in real world, packages of the same product are not identical. The features may vary because machines have their own intricacies and they not always produce the same thing. So the question is how we can build a system that will identify packages of the same product if packages tend to vary. So then we get into the notion of closeness. So it is clear that vectors of packages of the same product will have similar dimensions. That is, they will be close to each other, while vectors of different products will be far from one another. And I'm saying far and close in a quotation mark because we haven't defined what close and far means. And then the question is how we can define that. So we need to come up with something. So we need to define a notion of a distance between two vectors or how similar they are. And intuitively, we understand that the distance should somehow reflect the distance at each dimension. So what do we do? From the standpoint of a single feature or a single trait, let's say weight, it is easy to measure the distance because it will just be the absolute value of the difference between the value of that feature on object A and the value of that feature on object B. And we can extend its definition to all features of all subjects by summing the distance we found on each feature. So this is what you see in the bottom. We also can borrow the concept of a geometric distance to define the distance between vectors A and B by summing the square of distances on each dimension. And this is the Euclidean distance. And what we can see is that we have many ways, actually many ways to define distance. And indeed, in real life, there are many measures for distances, and this is not the only one. And we use them according to what a trait in the difference between two vectors they highlight. And this is something that students will meet in later courses. But for this course, we'll stay with Euclidean distance. And then we can go into what else can we do with vectors? Well, finding the distance between two objects makes sense if we talk about packages, but other operations, maybe can we add two objects? Well, or subtract. Well, that doesn't make sense for packages, but it might make sense for other objects. For example, let's say that we have some kind of a voice or a sound, a vector that describes sound. In this case, the sound may be described as a vector of variations of air pressure levels over time. And if we want to combine two sounds together, for example, then we just can add them together by adding the corresponding values of the vector. And you can see here the image of adding two vectors together, and you can also hear it. Let me see if I can, yes, here, and you can hear it. Just 1 second. This is the first one. This is the second one. And this is both of them together. And this is being done by adding two vectors, by adding two of these series of numbers. In a sense, what we are showing is that we're using mathematics to describe a general algebraic vector. And we can use it to define general operations that can be done on vectors and find general traits of vectors. And when we apply the abstract math concepts to a real-life problem, we choose the operations that make sense for that problem. But the strength of mathematics is the ability to define an abstract concept that is being applied through a large set of problems. So this is how a real-life problem is the drive for mathematical concepts and traits. Now we will talk about methods to improve students' learning abilities. So what can we do? We can explain the difference. So first of all, the problem is that students have difficulties learning math. And what can we do? We can explain to students what is the difference between learning in high school, learning mathematics in high school, and learning in higher education. And sorry. And we can provide students with method of gradual learning. They need to start by making sure that they understand the definitions, that they understand the whatever lemmas and concepts they have learned, and then they make sure that they understand how to solve, and they can do it themselves. They can solve. So we have a methodology to explain to students how to study math in a higher education settings. An important aspect of providing students with learning tools is in-pair learning. During lectures or recitations, we proactively ask students to work together on a problem. They use this opportunity to teach each other. We also provide students with suggestions as to what to do when they get stuck, and and if they're missing some prerequisite knowledge, we provide the prerequisite material, but we provide it concisely so that they won't have to spend too much time on understanding these concepts, and they can go back to the main stuff which is the material they're going to learn during the semester. Now, I want to emphasize the in-pair learning. This is an opportunity for the students to discuss the material and or to solve a problem with their peers. And this breaks the lesson and it engages students in a different and more proactive learning. This form of teaching where students interchangeably alternate between the role of a teacher and the role of a student is engaging and it is effective. The application of peer learning in the context of learning mathematics for first-year students is, however, quite constrained because we have a lot of material to cover and we have very little time to do so. So the way to do that is not to do that during lectures so much as during recitations. And the best thing, and this is what I did this semester, the best thing is to do that if you have the recitation and the lecture together, and that way you can break the lecture more effectively. Very often, so now we're talking about providing feedback to students that so that they will understand their level. I think that it's not only my impression, it's probably your impression too, that very often students have the impression that they have a good grasp of a topic. However, their impression is based of learning experience from the secondary or high school, and it is divorced from reality. Because they are unaware to the differences between studies in secondary schools and higher education, they think they know the material, but the true level is that they will not pass the exam. So for these students, we need to provide some way of giving them some kind of feedback as early as possible so that they will understand the true level and can take actions and mitigate the situation. Moodle has a great tool which is automated tests. They are very difficult to maintain and to work with. And they are now more. However, this is the easiest tool, the easiest and most it is you will find it in many schools basically, but what we want to suggest is the Stack platform, which and the advantage of the Stack platform that can be implemented over Moodle is that it makes it possible to test the algebraic equivalence of the answers of that the student provides, and that way students can write equations and not only answer multiple choice questions. Moodle is getting towards that, but Stack is still a better choice. And in-class work also provides students with feedback to their true level of understanding, and this is also good to allow students to understand the true level as early as possible. Now, as I said at the beginning of the talk, we need also to be proactive. We need to identify students who are at risk to fail and find ways to mitigate the situation and suggest them ways to mitigate the situation. So what we need to do is we need to do two things. One is we need to identify the student at risk to fail, and then we need also to provide them adequate help so that they will be able to recover. So first of all, how do we analyze? How do we find students who are at risk to fail? So we have many ways to do that, because students leave digital footprints in platforms like Moodle. And what we can do is we can find patterns that indicate a risk of failure. For example, low activity, declining activity level. And if we do the test, then test scores can also provide indications to the student's condition. So all of these things can raise a flag and identify students who fall behind. Once the students are flagged as being at risk of falling behind, there is a need to contact these students and check whether the indications that we basically have some indications, it's not necessarily true, whether they reflect reality. Now, here it varies among schools. Different schools can apply different methods to access these students depending on their staff and financial abilities. The easiest and less efficient way is to alert students electronically via an email. However, a more effective way would be to contact students personally and understand what they are, whether they are actually falling behind, and if so, what are the reasons for it. Reasons for falling behind are varied and might be related to external constraints. For example, problems at home, financial problems, and so on. So what we need is we need to provide for as many as possible, many situations as possible, some kind of mitigation strategies so that student can recover. For example, if students have a problem in learning. Some students have problem with learning abilities. There are some places where we can refer them to a counsel. If they have problems at home or they need to work, then we can suggest them to concentrate on certain classes and defer certain classes to a later time, and so on and so forth. And all of these mitigation strategies are dependent on the school and on the and on the culture and on many other factors that are individual to the school and to the student. So we began to use these real life examples, and now I want to talk about our experience. And so our experience when we present real life examples is very positive. So the responses from students are very warm. Students are engaged, ask questions, and they feel that this is more relevant to what they are doing. But in order for that to work, we need the examples to be light. It should be short, maximum 10 minutes, and not more than that. And it need not to be too mathematical in nature. And some of the examples that we're using are are taken from programming projects in second and third year of student studies. In-pair learning was very difficult to use because students don't have a convenient method to write mathematical equations on a shared medium. So we started by trying to apply in-pair learning, but we ended up either abandoning it or giving each student to work alone and then present the answer. And in the summer semester, some of us are beginning to teach to teach in front of a class, no Zoom. So we will see how this works. So we plan to use it more frequently next semester. Um, um, Frequent exams for some students, it was hard, but for others it provided a mean for further practice, and it did some of the work that was intended. So I have only 10 minutes left, and I want to have some time for questions. So if there are questions, I will answer the questions. Otherwise, I will talk about other examples, real life examples.
So this is up to the audience. I have one question at this point. So you mentioned that you're using, the frequent testing, and then, you're using automated testing, which means that the feedback comes as a function of the reply of the student. So your replies are accommodated to the mistake that probably the student is going to do. So
no. This is not the situation.
No? What does it mean?
No, I mean, automated means that it's being graded automatically.
Okay.
I'm sorry.
All right. This is something that, Moodle and all, the platforms.
Yes, yes.
I think the next step is like, in order to move to a personalized education, it's like, when we're talking about automated, like somehow using, let's say a machine learning or something like this, the system to provide the next question should be based on the reply of the student. So you can elevate the difficulty, or you can help him by sending, if he's going to do mistake, the next question will facilitate her way towards, the correct answer. This is like what did I think?
Yes, of course, but I think that this is something that would be very very inefficient to implement it in each and every school. I think this is something that maybe book publishers or other groups will develop, because it's a lot of development.
I would say that, if you have a lot of data, based on, the mistakes, or, if the university can collaborate on the main mistakes that the students they are doing, then I will say that, machine learning can help, in order to develop this, no?
Yes, but then if you teach math in one university, and then you teach math in another, calculus in another university, it will be pretty much the same, and the mistakes are pretty much common. So there is no, it's not efficient to develop two systems in two different higher education systems. I think that this needs to be more consolidated, in the sense that you will have, in a sense, what I'm saying is that it will be better to purchase something like that and not build something like that in the university.
And I have a second question that I have is like, from the moment that you have used in Holon these real life exams, and you are trying to present the same thing from a different point of view, from the application point of view. Now, how much? What are in numbers? The improvements that you have noticed regarding, let's say, in the exams, it will be very difficult to quantify. But regarding the commitment of the students, like how many you are starting, what we have observed, that we're starting, the face-to-face, or even, the online courses with, 50 students, and by the end of the semester, probably it's like 10 students, 15 students, like following this kind of exams. How much you have managed to keep, the commitment of the students to the course?
Well, it's very difficult to say, because the reason why students drop usually do not depend on the quality of the class, or whether they think it's relevant or not, but on external pressures. For example, if they have a midterm, I will have less students, regardless of how interesting the class is. And if they have a project to submit, they will work on the project. So I didn't feel a change in the number of students, but what I felt is the change in the energy within in the class. That means that they ask more questions. They're more active they suddenly ask questions that reflect an understanding, as opposed of just sitting and getting material, absorb material, you know, and that's it.
Mhm. Let's give the floor to my colleague, Professor Kavousanos. Professor Kavousanos, the floor is yours. Thank you, Nissim, for the answers.
Thank you very much. And sorry, I cannot turn on my camera because my connection is bad. So I prefer not to turn on my camera. Sorry for that. Dr. Harel, as I have seen, as I can understand, you have an engineering background. Is that true?
Yes.
It is true. Okay. Now, how often, is it common that in Israel or somewhere else, engineers teach mathematics? Because this is, I think, this is crucial.
You're right. No, it is not common. It's actually more the exception than the norm, and but the thing is that, and you're right, this is a big challenge. It's a huge challenge. But then the question is whether we that come from an engineering background can provide the material for math teachers, because obviously math teachers will not go into each and every detail of every application. But on the other hand, if we can do it concisely, then it will be easy. And if we will provide the material, if we provide a bank of examples and a bank of presentations and a bank of prepared lecture notes, then it will be easy for other teachers to adopt it, because the level of understanding in mathematics, in engineering that is needed in order to follow most of the examples is not high, and this is by purpose, because students don't know, even students in engineering don't know this material at this point. So you have to have the level. You don't have to. I mean, you must have present the subject at a very the engineering subject at a very low level, so that they will understand it. So I don't think that it will be a challenge for the math teachers. But again, this is the work of the engineers and the people from a life science background or whatever subject it is to provide these examples. This is not the job of the math teachers. I don't think that it will work if we will tell math teachers that this is what they need to do.
Thank you.
I would like to add that, I think that teaching, fundamental mathematics from the point of view, if you're an engineer or a physicist or life science, science is like provides, and you are not a mathematician, provides more, I would say, how can I say, fantasy, like you can connect directly the mathematics to the application. So I think that it will help the students to motivate it and love what mathematics they can offer them as a tool. Like I have found that the mathematicians, they have a particular way that they are teaching, and they are not so much linking, mathematics with the real examples and the real applications that they come with mathematics. This is my perception by following. So Nissim, do you want to go on with some real life examples? I have one more question. Like you mentioned that you're like, I truly understood that the energy, however, this energy can be transferred through the Zoom, but it can be transferred by looking, a lot of cameras on, or by a lot of questions that the students they are asking. But the group of the people that they stay together with you and they demonstrate this energy, what is the reflection of their success in the exams? Because on the exams, you can see, I mean, the people that they are activated, they are active within the classroom. That's why you are using Moodle. That's why you are using, and you are monitoring, their frequent and their commitment through solving the frequent testing. What is the percentage of these students on the final exams, and what are the percentage of students regarding failure or success that they are not active?
They usually they obviously have a better chances to succeed. I mean, I know that if students, usually, if students do participate, do their homework, they have a good chance to succeed. Um, so, so regardless of what I do, this is the situation.
All right, so it's just the energy then.
Yes, yes.
All right.
It's the energy, it's the interest, and it's. I think that the that
Nissim,
I think yeah.
please let you finish because
I think that the main thing is I think that the main challenge is not only to get them past the exam, because there are ways, you know, you can cram before the test and blah blah blah, and they will pass the exam. The question is what will happen in second and third year, and whether they will be able to understand or to apply the concepts they have learned in first year in the second and third year. Usually what happens is that they come to the third year and they don't remember anything.
Okay.
It is as if nobody taught them anything in the first year. And this, and I think that with a story, it's much much easier for them to remember the situation.
I totally agree with you, because by running this pre-calculus course here in the Department of Electronic Engineering, Hellenic Mediterranean University, you know, and this was the third semester that we ran this course using, you know, similar techniques as you. It's like the realization, the nice thing that, you know, I'm getting is the realization of the students. Why do they need mathematics, and how the mathematics can help them understand things that they have learned, you know, before 3 years.
Yes.
This is like the main impact. Yes, Professor Gabusanos, your hand is still up.
No, I have one more question.
Please.
One short one. Dr. Harel, you referred to in-pair learning.
Yes.
Is it something special about in-pair learning and not group learning? Why not group learning generally?
The question is, what is the best size of the group? I mean, if you have a bigger group, you will have freeloaders, and if you have a single one, then it's not working with groups. The thing is that what I found out is that in the setting of a class, usually because of the way the class is being built, and it's much easier to do it with a group of 2 as opposed of a larger group. A group of 4 is usually I mean, it should be between 2 and 4. But more than 4 is inefficient in the sense that you will have people who will not participate. They will not feel that they need to participate. But then the thing is that because you have, you know, maybe 2 people are sitting near each other, then it's easier to do it in a group of in pairs than in larger groups. But in any case, more than 4 is not is usually doesn't work.
Thank you.
So Nissim, do you want to go on with more?
Yes, if we have time, yes.
Go on.
If we have time.
Yeah, I will try to combine, because, you know, the other speaker, you know, on the other room is ready to finish. So go on.
Okay. So this is an example of linear combinations in images. Again, this is linear algebra, where we have linear combinations, and we present it how it's being done on images. We can in calculus we can show why we need the area beneath the graph by presenting concepts from machine learning. The more the area, the greater. And here we're comparing two machine learning algorithms. The one that has more area is better than the other. Sorry. This is more from analytic geometry. how do we know how the computer can determine whether a a point is being clicked inside a triangle or outside the triangle, and we also can use Lagrange interpolation of polynomials in order to show how we can share a secret among many people. That's it. So thank you very much. And if you have any other questions, I will be happy to answer.
So Nissim, you can handle the questions. Please direct the questions directly to Nissim for 2 moments.
Okay, so thank you very much. And I hope that all of us will be healthy in the next few months.
Thank you, Nissim, for the presentation.
Thank you.
Okay, so are there any questions? I just ask a question, to the speakers, the other speaker. Are there any questions? So if this is the case, I would like to thank very much, Nissim, and I would like to welcome all of you to follow item project. I can send you all the information if you have requested to follow, the first results that we have, and we would be very glad to have you on the last talk before the summer vacations within the framework of the Athena Colloquia talks next week with a colleague from United States, Emine Selik, that is going to speak about project-based learning. Okay, thank you. I was just, asking, replying a question to the other event.
Okay, thank you, Kostas. Thank you, Nissim.
Thank you very much. Bye-bye.